In this tutorial, we will create a roof using megascans tile assets. So what I have done, I have imported a single tile from megascans library like that. So there's a bunch of them. This is just a basic one like that. And after our operations, we should have something like this, where we have taken input geometry, which is my base roof, something like this. And I have basically just, for every one of these primitives, I have copied these roof tiles to something like this, and I have cut the seams on every one of these parts. So basically, so that we have a good connection points where we can put our ridges at, like that. And anything inside it is actually instanced primitive. So we have only cut geometry where it's necessary for the seams to be connected like that, and everything else is instance geometry. So there's a lot to it. So let's get started. And to follow this tutorial, you will need to do a little bit of a setup, because of the previous video that I did I did some setup for the input geometry. So input geometry was something like this, and in this for each loop, I actually went ahead and orientated every primitive to the positive x-axis. That's going to be my starting point for laying out the roof for the previous tutorial, which I'm going to link in the description. And basically the same setup is also required for these megascan styles. So basically what I'm going to do is create kind of like a switch node, where in previous video I did this this way, where I generated these tiles basically on my own. But if I want something like a megascan tile, which is like here, I imported megascan tile. So this is going to be a different, since the rotation setup is the same, I'm going to put down the subnetwork and connect it inside here. And we're just going to switch between tile generation from scratch and megascan style. So yeah, so if you're interested only in megascan tile creation, just go ahead and watch up to the certain point the previous tutorial, which I'm going to link in the description, where we basically just rotate every one of these primitives. So yeah, so let's just assume you have this setup correctly. We have rotated the incoming primitive, and now I want to go ahead and lay out my megascan tiles. So let's go inside, and let's actually go ahead and connect this tile also to the subnetwork. So inside the subnetwork, I want to make sure that I also get this tile. So this is the compile block, also going to include this. So we're going to fix that later, and whatever the problem is going to be after that. For now, let's just go ahead and focus on actual logic that's going to create these tiles. So connect also the megascan tile. So what I did is actually went ahead and rotated it by 180 degrees, because of by default it comes inside here, and when I laid out it's well, it wasn't correctly set up. So yeah, so just rotate it. So you can anyway rotate it anyway, because of the different tiles come in different rotations inside it. So yeah, so that doesn't really matter. So let's go inside the subnetwork, and first thing I want to do is actually go inside my roof tiles logic, and actually go ahead and copy the base roof in the grid that I basically aligned to the roof. I want to go ahead and copy this grid with a match size. You go and copy and paste inside here. So incoming is going to be this. So output, we can put it down. So this is just going to put my grid that's going to be aligned. Make sure that let's put down null roof reference, let's call it, and let's copy this null, and the second input is going to be my tile in roof. Let's call this also in, because we might want to like rotate this tile inside this network, so it's better naming convention. So roof in, we have now my grid is basically just because of the roof. So this is in this case my roof is also squared. It's a rectangle, so this way the grid looks basically the same. But if my roof wasn't rectangle, it would be like a triangle. We would still need probably the smallest square that can fit inside this. So that's why we are actually using the grid, and then we are matching the size of it. So yeah, so this is all done in the previous tutorial, but for now this is always going to be anything inside this network is going to be actually a new logic. So first I want to put down the wrangle node, and to demonstrate what I want to do with this in this wrangle node, let's imagine this is my roof, this is my one surface of the roof, and these tiles are laid out like that. And since our roof can be whatever the size it is, imagine every row is basically a new row of tiles. Chances are that this is not going to fit exactly amount of times. So basically, maybe it fits like 1, 2, 3, 4, 5, 6, 7 times, and maybe basically the height of it doesn't allow us to get another row of tiles. And if we, let's say, we have this edge and we start to copy also on this edge, it would be basically ruin the symmetry of all of these, and this row would basically overhang this one too much, because of the when we are copying to points to these tiles, it would be basically, it would not be the even distance between all of these, because of the height of it can be dynamic. So I want to make sure that I take the tile's height that I'm going to copy, and I want to make sure that whatever the times it's going to fit in, and whatever the time it doesn't fit exactly amount, I would make sure that I just take these 2 points and move them upwards. That means that this tile is going to fit one last time also above this. So I want to basically extend this these 2 points to the to fit another no, basically the last tile row. So this is what I want to do, and this is good because since these points are always the same, and to make sure that they are also the same, what you can do is put down a sort node, and in this sort you can just sort it by y-axis, and this means that these 2 points that you want to actually move offset is always going to be 3 and 2, and this is why in this wrangle you can just put down a 2 and 3 as a group like that. So I want to let me open this up. So I want to get my tile height. So this is basically, we can dynamically change the tile height. So this makes sense that we want to create a float. Let's call this tile height, CHF. So we have our tile height, and then we want to get the bounding box of this square. So vector. Let's call this bounding box size. So it's going to give us the size of it. So get bounding box. That's going to be get bounding box. That should be size geometry 0, like that. So now I want to see how many tiles fit right now inside here. So this is going to be a float, and we just want to tiles fit is going to be our bounding box size dot y, because of the y-axis. We just want to go ahead and divide it by tile height that we want to get, like that. And now to see how many tiles fit, we want to get the remaining, basically the whole number of this float would be the amount of tiles fit, and the fraction of that float would be the how much of we still need to get to the next size, to the next tile. So this is where actually going to get create a float. Let's call it height to add, something like this. So I want to, so we know that one basically float one would be the whole tile in here. So that means you want to subtract the from 1 the fraction of this basically the fraction of this tile fit. Let's do this 1 subtract, then let's do this all in like that. So I want to get the fraction of the tile fit. So this would be something like maybe 0.5 that is actually going to return. And I want to subtract 1 from that, because that would be the basically the fraction of how much you want to add to it. Then I just want to go ahead and multiply it by tile height, like that. So this is basically the remainder that we want to add to our y points. And all I want to do is v at p dot y plus equals height to add, like that. And you might have noticed that I did the wrong parentheses. What I want to do is subtract 1 from the, basically I want to subtract the fraction of the tile's width, 1 from that, and then multiply by tile height, because of that the basically the how much more we need to still add to that one. So I did the wrong parentheses. So make sure that you did it correctly, and then just add the height of it. And this should basically make sure that we are always adding these values. And this should make sure that basically the y value, well, basically the bounding box of the height will always divide equally with this box, like that. So this is well going to be really useful for us to when we're going to have to Boolean these shapes out. So yeah, so that's done. Now let's actually go ahead and actually start cutting this geometry up. So this is where we're going to do another wrangle node. So make sure that you're running over the points inside here. Attribute wrangle. So now we want to just go to the details. We just want to do this one time. And I want to get the tile height parameter from the top of it, from here. So this is where I want to go ahead and go to float tile height equals. This is very nice because we can actually go ahead and reference the parameter outside this wrangle node. So let's call this height adjust. And then just copy this name, and then you just dot slash in this node, and in this node it's called tile height. Tile height. So now we're referencing parameter that is outside this wrangle node. And just to make sure that it works, you can actually go ahead and printf and tile height. You can see we are 0.61, 0.6, yeah. So this works. So it's always good to check, because when it's not working, you will think why it's not working. So what to do is now divide this square to the same length, where we're going to actually go ahead and copy, basically create a polylines in this basically points at equal distance between them. So this is where the our bound. Let's start by getting our bounding boxes. So vector. Let's call this bounding box max. Get bounding box max. It's going to be 0. Let's copy. Let's call this our bounding box min. And then I just want to bounding box size. Size is going to be get bounding box size. Size is just the size of it. Doesn't really matter where the position is. Just how high can width wide is the geometry. So and now let's actually go ahead and calculate the row count. So this would be let's call this an integer. Let's call this row count. So we know that we have just our box. What we can do is create a int, which is basically just going to round to the nearest. I think it's going to be float. It's going to basically round to the nearest float, which we probably don't even need because of the because we know that these values are going to very nicely actually round. So let's get the bounding box size. Bounding box size dot y, and then we just want to go ahead and divide it by the height, like that. and then you just so this is going to be it's going to give us squiggly line because of the it's always division is going to give us because these are floats, it's going to give us a float value. Actually, take a look at what's the value of this float is. So it should basically always be basically the same, very close to this float should be always close to the you can see it's even though it is float, it basically shows as an integer inside the log. So we just want to make sure that it's always going to be an integer. So this is why we just want to cast it to the integer. So it doesn't show these squiggly lines. It doesn't really like that. I deleted this. So yeah, so we just want to cast it to the integer, and now we know how many rows we actually want. And now we just want to go ahead and create the for each one of these. We want to go ahead and create our points. So put down a for each. So we just want to for each row count. Let's call this integer. Let's call this a row. So now I want to get basically the opposite positions of these two edge points, basically of these edges. When you get the positions of these lines, and just go ahead and increment based on our loop count the position that it's going to actually be basically positioned. And it's actually pretty simple. What I want to do is want to get the height of it for every one of these rows. So it's going to be float. So let's call this a row height. It's going to be our current row, and since we are starting from the 0, so we do not want our because we already have a row at the 0 at the primitive, we just want to start with the 1. So this is going to be row plus 1. Let's do this in like that, and I just want to go ahead and multiply it by the tile height. So this is a position where the points will be on the y-axis, and to get the rest of it, we just can construct a vector. Let's call this position 0, and since it's going to be vector, we have to use a set. So I'm going to use a bounding box. Now these max and min bounding boxes are where we want to set our points to. I'm just going to write this out. And so bounding box max dot x, bounding box min dot y. So this is basically the minimum. Since we want to start adding these values from the bottom of it, we want to get the minimum. So basically the position where our square is, which is always going to be at here, and then we just want to add to that position from the starting point, because for every loop we are actually increasing that position. So you just want to go ahead and start by the bottom value, and then just add the row height like that. And for the bounding box max is going to be bounding box for the z is going to be max.z like that. And then we can just go ahead and copy. And we just want to get, instead of the bounding box max, which is bounding box min inside here. And that should be basically it. We have our 2 points. Let's actually go ahead and save. Positions is going to be 1. And now to add these points, what you can do is add point 0, and point number is going to be position of these points. You see, we are adding these. So there's a couple of problems, but I'm going to show how to fix them. And then we just want to add to the opposite point, which is going to be 1, like that. You can see we are actually creating the last points also, but which basically which we do not need. So this is where we actually can just go ahead and basically the row count, calculate our row count and subtract 1 from them, so that we do not create the last row of the points like that. But basically this should make sure that we are always, you can see we are basically always creating these points equally like that. So this should be done for this wrangle node. Right, and now I need to go ahead and connect the opposite point. So I'm going to put down a sort node. And this is actually very simple. I sort by y-axis. You can see we are sorting by y-axis. This means that these two pairs are always going to be opposite of each other. And we can use that to just go ahead and create these polylines. For polyline creation, what I want to do is put down a wrangle node. So in this wrangle node, I want to connect it to the second input, and I want to make sure that I run over details because we have no geometry inside here. So I just want to use these points as a reference to create my own polylines. So go inside the code. And now that we have actually sorted these points, we know that these are actually going to be opposite. Basically, the opposite ones are going to, basically the point pairs is going to be the polylines that we want to create. So let's go ahead and make sure you're running over this. So let's get the number of points inside our first input, like that. Let's call this PT. 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 Now make sure that we also only run our polyline only to the opposite points. So we're going to use a modulus since we have used the sort node. If PT modulus of 2 equals 0, that means that this opposite point is going to be an odd number. That means we can create a polyline. So let's create the position of these points. So it's going to be a vector. Position 0 is going to be our point. 0 attribute name is going to be our position. PT name is going to be PT. And then the position 2 is going to be, position 1 is going to be PT point plus 1. So it's going to be our opposite point. And now I want to add these points. Let's restore these because we need for our polylines. Let's call this PT0. It's going to be add point 0, and point number is going to be a position. Where I want to add this position 0, like that. And then just go ahead and copy this, paste inside here, position 1, position 1, like that. So we have created our points. So in position we have to use, my bad, we have to use a position 1 to fetch the position of these points. So you can see we have created a new point, which is just these points, like that. And now what I want to do is create these polylines. So what we can do is add prim. So the type is going to be polyline, and then the position, basically the points from what we want to create this polyline is going to be PT0 and PT1, and that should be basically it. Now we have created our polylines, and they always should be the exact distance between them, like that. Okay, so that's that. What we can do is now put down a resample node, and this is going to basically just calculate how much of a, so this is good because we can basically create how many tiles we want depending on what tiles we want and what overhang, basically how they are created, how we want to how many tiles we want. So that's pretty simple. And now I want to do a little bit of an intersection detecting and all of that stuff. So let's do that. Now that we have our points that we can create the copies to, let's do that. Let's put down a CopyToPoint. Let's put down CopyToPoints. So we need geometry to copy and points to copy to. So points to copy to is going to be our resamples, and then the input tile, megascans tile, is going to be the second one, like that. So you can see, since we do not have any up or normal values, it's just going to be copied as it is imported, like that. So this is not the best way to do that. So I go to is put on transform, and just to make sure that it's we get a good representation, just to orientate it to the x-axis by 90 degrees. So now our copy should look something like this, and then we can go ahead and play with these values with these and our height adjust, which is the tile height. So make something like that it looks correct. Maybe want even a little bit more of overhang like that. So let's say I'm happy with this tile layout like that. And to visualize our roof, what I did is change the primitive that I want to template. Basically create a roof for. You can see this is the actual roof that comes inside this subnetwork. You can see what I want to do is just cut out this part of the roof. So this is where we want to go ahead and detect the intersection between this input roof and this CopyToPoints geometry, which is not instance because we want to detect them. And once we have detected them, we just want to go ahead and Boolean only those shapes, and rest of them we want to leave them as instances. So this is a little bit of a workaround for the amount of points you have, because let's say you have a huge roof. We do not want to go ahead and copy all of these geometry to the every one of these as a not instance. So anything that's not going to be intersected with the edge of the roof is not going to be its own geometry. It's just going to be an instance of the input tile. So this is the neat trick that I want to do. So first of all, for the intersection analysis, I want to use a Boolean node, and for the Boolean to work faster, I do not want to intersect analysis with this geometry because it's way too big of a geometry. So what I can do is actually go ahead and take this grid, which is already aligned with this tile, basically on the x-axis. I just want to match size with it. Just take this grid, match size with also with this one, and by default it should be like that. So none, y, min, that's fine. I will scale to fit and uniform scale turn off. It should basically make sure that our proxy geometry of this grid should basically just fit inside here. And this is the actual geometry that I want to copy to these points. Just put it inside like that. You can see we are overlapping all this geometry, and you can see that if I put down a Boolean node, I want to intersect analysis, this one, analysis for this, and the input for this should be my basically the input roof, which is this one. I just want to go ahead and extrude it. Poly extrude. Actually, let's do this a little bit neater because of the cross wiring all of here already. For the Boolean, I just put down object merge. Where is it? Object merge. Oh, it's here. Let's call this roof in. I just want to go ahead and take this input roof and copy so that I don't have these wires. And if you're using one of my tools, you can easily reference this geometry like that and just put inside here. So you can see it's not exactly the same because we want to poly extrude. So I want to extrude. I just want to intersection. So I just want sides of it. So I want to. So that should be the sides. I do not want to. So wait. So why is it giving me also back? I had templated. So like that. So I have something like 0.5 should be pretty safe for us to use. And then I just want to match size with these CopyToPoints. Match size. So I want to move this to this. And for it, I do not want to move it by y because y is already correct. I just want to move it by x. And x should be, I think it's center. So x should be center and d should be none. Because I do not want to move, because this roof is already in a correct position. I just want to move it to intersect with this geometry, like that. So this is my intersection geometry. I'm not sure where I should put it. Maybe something like here. And then the Boolean should do like that. And this Boolean should just detect. And I just want to, I think it's A, B polygons. let's take a look at the groups. You can see right now, you can see we are basically getting the primitives that are intersecting with these geometry. So this is basically primitives that we're going to copy to, that we want to Boolean, and the rest of these points inside it we do not want to basically copy as a geometry. This inside is going to be actually basically instances like that. And for this, to make sure that these go away, make sure that you so input B is not a solid, it's a surface, and the input well, I guess the input also A is also a surface like that. So because they do not have any thickness to this like that. Okay, so detection is done. And now that we have our intersect primitives, what I did is rename these to intersect prims. I want to reference basically all of these calculation of the intersection back to these resample points that we are going to actually copy to points for the instances that we actually these points are still needed for when we are actually going to copy our real geometry tiles. So what I'll do is actually create basically copy from this geometry some attribute to these points so that I can refer to these points back. So put down a wrangle node. It's going to be very simple. E at I'm just going to call it ID equals at PT_num. So the current point number is going to be its ID number, which is very nice because once we are boolean it out, you can see it's going to have also a point attribute, and for point attributes it's going to be four zeros, 4 ones because of the 4 points for every one of these primitives. This is how we can basically reference back to these points. And then I just want to split these points to the points that we're going to instance, and then once that we're actually going to Boolean out. Put down a wrangle node, connect these two, and we can just go ahead and put it to the detail wrangle. And in this wrangle, for the second input, I actually want to go ahead and split this geometry. So inside here, I just want to get my intersect primitive geometry. So I know that these all are going to be intersected. And in this wrangle, I just want to, let me open this up in editor. So I want to get all the unique values of the ID attribute. And this is there's a useful function. Let's create let's call this Boolean PTs array. And there's a unique vals function. So for geometry it's going to be 1, attribute class is going to be point, attribute name is going to be ID. So this is going to get, since we have a lot of duplicates, because we have for every point there is going to be 4 of these. So you're just going to get the array of the unique points like that. So that means that in these points are point values of this geometry like that. So inside here, then you can just run through every one of these points. So for n points of first geometry, let's call this PT, and PT. And then I just want to go ahead and if we find this geometry, basically if we find this point number inside this array, that means that this is let's go Boolean point, and if it's not, it's an instance point. So if find in a Boolean PTs, and the target is going to be the PT. So basically, if it finds, it basically gives an index in that array. So if it finds it's bigger or equal 0, because 0 can also be the index of it, I just want to set a point group. Point group. So name is going to be, so let's call this Boolean PTs. Point number is going to be PT. Value 1. Mode, we don't need that. And then we can just put down a continue to go for the next loop. And if it's not, basically if this loop is not triggered, I just want to set the point group for the instance PTs. PT, and that's it. And if you take a look at this geometry, you can see we have 2 point groups. You can see Boolean points are the points inside and are basically around like that. So yeah, so that's good. So another thing that we want to do is actually make sure that since we have a lot of overhanging points for the instance points, you can see that instance points are also, we know that inside these we all definitely want, but there's also a lot of points outside of it. So we want to get rid of these points. So let's do that. And to delete the points that are outside the roof, what you can do is actually go back to the poly extrude where we boolean out, where we detected the boolean points. We can actually go ahead and put these also output front and back, because this shouldn't actually affect the groups of the boolean, but it's going to actually give us our points to be checked intersection with. So basically, since now our geometry is closed off, if outside points actually basically intersect with the roof geometry with this one, that means it's inside, so it shouldn't be deleted. And if it doesn't, we should delete it. So basically, after this, I want to put down another wrangle and check for the intersections. So put wrangle, and for the intersect geometry, just put it as a second one, like that. And then we can actually go ahead and run only through the we just want to run through the instance PTs. Let me open this up. In this code, we just want to, since we are using intersect, it's actually going to write some values to the some vector. So vector position, vector UVW. So this we won't use them, but the function actually uses this. So an int has intersection equals in intersect intersect, right? That geometry is going to be so 1 because of this one. So group, we don't need group. So the origin is going to be our current point position, v at p. So direction, we know that it's always going to be on the positive x-axis. And since direction is also direction also needs to be basically we have to, since the it also has to be direction plus the how far to search for. So that would be the magnitude of the vector. So it's going to be just pointed to the x-axis and just multiply by something like 100 to be safe. And then we can just write these position and UVW intersect position like that. And then if the has intersection basically is bigger or equal 0, so basically the intersection this returns the primitive that it intersects. So the primitive can be 0 and can be more than 0, but it cannot be and I think if it doesn't find it, it's basically a -1. So basically if it has found it, actually let's do this as a smaller, or if it's smaller, or if it's basically if it's smaller than 0, like that, then we want to go ahead and remove it. Remove point 0, and point number is going to be at PT now. Actually I should actually check actually go ahead and check the I think the intersect, it might only return the so what it returns. So returns intersect the primitive number or -1 if there was an error or rate didn't hit anything. So okay, so -1. Actually, to make it very clear, if has intersection equals -1, we just want to go ahead and remove that point like that. So you can see basically we have removed these points that are that were not part of the basically that are outside, and we do not need to instance them anymore. So okay, so this is a good place to start cleaning up this network. So let me do that, and we will return to rest of the network creation. We can split between the group that we just created. So let's say we are Boolean shapes. So let's put a no node. Let's call this Boolean PTs, let's just copy, and inside here will be instance PTs, like that. So for the Boolean PTs, we just want to go ahead and copy 2 points. I want to copy to these points. I want to object merge get these tiles. Let's rename this transform as a tile. Inside here, I want to put down an object merge. I just want to select this, and just want to object merge this one, so that I don't have to bring wires all across the network. So you can see these are my tiles, and I just want to go ahead and Boolean these out. Put down a Boolean. So the base is going to be this, like that. And what I want to do is actually, I think we can even use this geometry like that, which is a match size geometry. So let's call this something like a, so what should we call this, like a roof cutout shape. And just going to put down the object merge, and we just want to go ahead and get this node. So again, if you're using one of my tools, you can easily object merge these shapes. You just want to Boolean this out. So let's generate, and by subtraction it should, so how does it, so by subtraction it's actually not what we want. We want to, I think that would be an intersect geometry like that. Yeah, so you don't want to get anything outside, we just want to intersect it like that. So you can see this is already looks pretty good. One problem with these normals after the Boolean node are a little bit crazy, so we definitely want to fix these. But we're actually going to fix these once we have actually rotated this roof back to its appropriate position, so like that. So, but you can see already how it would work. So we copy the points, we do not instance, and we can just create another copy to points. We just want to copy to point the same tile, and inside here we just want to copy to the instance point, and we just want to instance these points like that. And let's say we merge these together, just as a demonstration. You can see we are getting this effect where anything that was cut out is being is not instance. Anything inside it is actually instance geometry like that. You can see I guess this should, oh okay, it is actually cut. So depending on the resolution of the how well this proxy geometry can actually detect the intersections correctly, I mean, it should work pretty good most of the time. It's not going to be perfect, but you can see where there's a little bit of a cut. That means this geometry needs to be not instant like that. So this is for demonstration. Let's actually delete this. We just need to now package all this information and bring it back to up on the subnetwork, and then rotate it back and do our fun stuff there. And that should be the end of the tutorial, so let's do that. And now I want to think a little bit more about how I actually want to use this tool. So this Boolean operation actually takes some time, depending on what's the geometry, how intense it is. So it can be very annoying to actually fine-tune the distance between the tiles that you want to copy to. So this is where I want to create kind of like a switch node, which is going to basically switch between the instance points, where instance points are all of these points, and they are not separated by Boolean point and instance points. And I just want to, as a visualizer, to see the distance between the tiles, to see visually that it looks correct, and only when I'm sure that I like the look of it, then I can just go ahead and switch it to the Boolean. So this is where I actually want to create a little bit of an option for me. So let's put down a switch if node, and so I want to basically combine all of these points as its own group and bring it back to roof generation where I'm going to copy the points. So I'm not going to create instance points, instance geometry inside this subnetwork because of the rotation, because of the instance geometry doesn't like this method that I'm using for the transformation of geometry. So I did some testing. So I want to basically I move only the points to its original position and then copy to those points this roof geometry. So this is where I just want to get the points out of this sub network. So what we can do is actually put down a group node. So once let's merge these together. So this is going to be option for us to when we are not actually going to Boolean all of these out. Just connect this inside here, just a point. I'm just going to replace the existing. I'm just going to call this instance PTs, like that. So instance PT should be basically all of them. If enable base group, and you take a look at it, instance PT should be 1, 2, 4, like that. So this is going to be option for us to when we do not want to Boolean it out. So this is going to be probably the, well, depends on the toggle that you're using. But for that, to make sure that it's, to make it consistent on this side, basically when this is 1, we do not want to Boolean. And when this is off, we want to Boolean. So inside this Boolean, we want to still bring out the instance points along with the Boolean out geometry. So put down the merge node. And we can just take these instance points and like these. So you can see we have instance points, instance PTs, and these instance PTs, basically all of them are together like that. So this looks good. And we can just connect this inside here. And then we just want to do a little bit of a cleanup. Group delete. So I want to delete the groups, all the point groups except for the instance PTs. So just put down a caret. Oh yeah. So instance PTs will not be deleted like that. And depending on whether you're using these or not, like that. So there's a couple more options that we want to use afterwards for these, for cleanup of the edges. But for now, let's just get these out of this subnetwork. And one more thing I almost forgot to do is actually put down an attribute transfer node. And I want to object merge. And I just want to take this roof, input roof, because of the way that it works, this generation, we are actually storing the transforms that we are doing as a detail attribute. I just want to make sure that I actually carry these on because of the all of these operations, and this is basically at the end of it is basically a new geometry, and the attributes do not detail attribute does not transfer over all of these operations. So I just want to transfer it from the original geometry. So roof in, object merge it, and I just want to go ahead and I just want to basically all the detail attributes transfer back to my points like that. And then once you have done that, it should be basically the same thing. We have rotated back from the previous tutorial like that. And for us to correctly orientate these megascan styles, we need to create a couple attributes for these points. So I'm going to put on Wrangle node. What I'm going to do is call this transfer. Let's call this transfer up vector. So we need up and normal vector for us to correctly orientate this geometry. So the up vector is going to be normal of our primitive that we are looping over. So this one. So just put inside here like that. And this should have a primitive normal, and normal is going to basically point perpendicular to the surface of it. So this is going to be our up vector for the CopyToPoints. So v at up equals, we just can normalize our prim attribute that we're going to get from geometry 1 input, and that's going to be normal, and the primitive normal and primitive points is going to be 0, because for every loop there's only one primitive, so we can use, we know that it's always going to be number 0. If you take a look at the up vector, you can go ahead and select it. You can see it's perpendicular to the surface of it, like that. And now I want our normals. So in for the group, we can put it for the instance PTs. So this is the group because there might be, so in this case, we are basically all of it is, there are no Boolean geometry, but if there is Boolean geometry, we do not want to set any attributes on that geometry. We just want to put on the points. So I'm going to show how it works, but just to know that, make sure that the group is, we want to instance PTs affect only those points. And for the second normal attribute, let's put down another Wankel node. Make sure that we are also running over the instance PTs. So inside here, I just want to get the cross product of the positive y vector and the our normal, like that. You will see that it's basically going to point every one of these to the next point, like that. So let me just do this and you will see how it actually looks like. So the cross product will always return the vector that is perpendicular to the both input vectors. So let me v at, call this normal, equals cross product of the v at, so we have our up vector we just created, and this second one is going to be positive y vector, 0, y, and like that. And that should be it. Let's take a look at it, our normal. So our normal and y. So the up vector is outwards, and you can see our normal is pointing to the next point, like that. If you take a look at all of them, you will see that this is giving us this kind of a framing, and this is good for our CopyToPoints node. So now we have our attributes set up, and if you go to this here, what I did is basically did a split between, because we do not know whether we are boolean this out. We just want to get the points and we just want to copy the tile to these. If you take a look at CopyToPoints, like that, it should look something like this. So you might need to go to your input tile and rotate it as you want it. So let's say we have rotated like that, and you want a little bit of a slant. You can go ahead and rotate your tiles from the input geometry, like that. You can see if it needs a little bit of overhang, like that. But you can see, make sure that you are actually instancing these points, because we are not boolean them out right now, to see that the distance between them are look correct. And this should be, let's say I'm happy with this, how it looks, and now I'll say I want to go ahead and boolean this out. So let's set up the boolean. And now to check out the other way around, so what I did is create a boolean node where I can select whether I want instance only or boolean also. And if we are correctly using all of these instance PTs, it should basically look the same for all of them. Basically it should work with these groupings only with the groups on these points, like that. And once you have let's say you want to boolean, so let's see, boolean operation is going to take some time, but after your for each loop you will see that you have basically cut out ends of it. You can see we can put some ridge on it to hide the seams, but you can see we have correctly created kind of like a hole and around it and around with it this kind of geometry, and then we can just split it between the geometry and instance points. And then we can just copy the points, instance PTs. We don't even need this group, because inside here it's only instance PTs, like that. And then if you merge these together, you can see you can't really even tell the difference between the instance points and the geometry points, and between the actual geometry, like that. And one last thing that I wanted to show is how can we make sure that we do not cut the bottom of the roof. So when you're creating your roof, you might want to keep the last tile also intact, like that. So you can see here the roof is such size that it basically cuts a little bit of a little bit of it and leaves it like that. So it's not the best look for this tile like that. So what I did some experimenting, and let me go to the subnet record of this. What we can do is actually, when we are getting our roof in, we are poly extrude, and when we are basically copying our proxy geometry of this, what we can do is, I already tested it out, what we can do is basically put out the normal node and basically blast any geometry that is basically which normal is -1. So make sure that you create the primitive normals inside here, and you can delete the primitive that are -1, which basically points downwards, which means that basically the base of our roof, like that. And when you are booleaning it out, you can see it's going to select only the intersections on top of it. So you can see before and after. So that means we are not going to delete these, basically we are not going to try to boolean the bottom parts of this roof like that. If you take a look at the result of our modification for now, you can see that it almost works. You can see that the last row is kind of a cutoff. This is because of the intersection precision issues. So let's go ahead and fix it. So go stand this up network. So the fix is pretty simple actually. So once we have created our intersect primitives, we create our points. Basically intersect, basically the points that are Boolean and intersection points, basically an instance point. You can see that in this instance, basically where we are checking the intersection, basically since our geometry is sitting right on top of these points, you see it's kind of a precision issue. So whatever the float value rounds to, you can see that it basically says that, okay, this point is actually outside and it is being deleted with this intersect group deletion. So what I did is basically put down normal node just like before, and I just went ahead and extruded it by -0.01, and that's going to make sure that this point is going to be inside when I'm going to check it. That means it won't be deleted, and this should basically fix it. The whole row, there's still going to be kind of these cutouts because of the sides, but if you take a look at our base geometry, it should be pretty look pretty similar to what we are having as an input geometry like that. And since we are not booleaning out the very bottom of it, you can see that also for the top roof it has left this instance strip also. So there's a bunch of ways for us to fix it, and I don't think I'm going to do this in tutorial, but you can think of like checking the normal of this roof. If it points upwards, then switch between geometry, or we can actually create the entire attribute to maybe to signify whether you want to cut off at all sides or the bottom, or leave the bottom as is, like at the bottom of it. So there's a bunch of options for us to choose to use to kind of control the geometry. So yeah, but that's for your implementation on this, how you want to work with it. I'm not going to show it. Okay, these tutorials already basically showed the most important part of it, which is the copying of these and then booleaning it outside. So yeah, that's it for this tutorial, and see you next time.